do one more example, calculating out area and polar coordinates using this equation right here, this formula, integrating 1 times r dr d theta over the region involved. Find the area of this region, slightly shaded here. What's going on here? These are both circles of radius 1. The lower circle is centered at the origin. The upper circle is centered at the point 0, 1. We want the region inside the upper circle, outside the lower circle. How do we do this? We need to come up with equations for both of these circles. So equations in polar coordinates. Of course, the lower circle has equation in polar coordinates r is equal to 1. As for the upper circle, the circle of radius 1 centered at the point 0, 1, you might remember this off the top of your head from polar coordinates and calculus 2. If you don't remember it, we can rederive the answer here. How do we do that? Well, this circle is going to have, we start off with xy equation and convert it to polar coordinates. This will have equation x squared plus y minus 1 squared is equal to 1. So this is equation of a circle centered at the point 0, 1 with radius 1. When we expand out this multiplication of y minus 1 squared, we get y squared minus 2y plus 1 is equal to 1. And this is good for a couple of reasons. X squared plus y squared, that's equal to r squared. Those ones cancel out. And then minus 2 times y, we know y is r times sine theta. So r squared minus 2r sine theta is equal to 0. R squared is equal to 2r sine theta. Divide out by r, and we get r is equal to 2 sine theta. Okay, so that is going to be the equation of this top circle here. Okay, we need bounds on r and theta. How do we come up with these? Well, let's realize that for a fixed value of theta, like this right here, those are the r values involved. So r values start when we hit r is equal to 1, and they stop when we hit r is equal to 2 sine theta. So those provide our upper and lower bounds on r. Now as for theta, okay, so we should be able to see here, there's 1 theta value, there's 2 theta values for us to figure out. Those are the points where we start and we stop. Now we just have to figure out what theta values those correspond to. How do we do that? There's a couple different ways, but maybe one of the easiest is, well, this point right here and this point as well, they're the intersection. So we're looking for the intersection of the two circles. One has equation r is equal to 1. One has equation r is equal to 2 sine theta. So really this is asking us for, or if we are satisfying both of these, we want 1 is equal to 2 sine theta, or sine theta is equal to 1/2. And the two solutions for this are theta is equal to pi over 6, and theta is equal to 5 pi over 6. So those correspond to, pi over 6 corresponds to the first theta value, 5 pi over 6 corresponds to the second theta value. Okay, so this is our setup here. Okay, let's crunch in. Let's crunch in here. We are integrating theta from pi over 6 to 5 pi over 6. R runs from 1 to 2 sine theta. I'm just copying down these bounds right here of the integral of 1 times r dr d theta. Okay, what do we end up with? Integral of, let's see, antiderivative r becomes r squared over 2. Plug in r from 1 to 2 sine theta, d theta. So this is, okay, plug in 2 sine theta here for r. We would get 2 sine squared theta. Plug in 1 for r, minus 1/2 d theta. And let's see here. Sine squared theta. We should know sine squared theta is equal to 1 minus cosine of 2 theta over 2. So 2 times this minus 1/2. This is equivalent to 1/2 minus cosine of 2 theta. Okay, so evaluating this antiderivative here, theta over 2 minus 1/2 times sine of 2 theta, plug in theta from pi over 6 to 5 pi over 6. And if I haven't screwed this up at all, you should end up with 2/3 pi. So there's another example of finding the area. I mean, the calculations are relatively straightforward. What's the tricky part is coming up with these bounds. Once you get the bounds, you should be all set.